I'd like to begin, Richard, by asking you to read the first paragraph of the first chapter of The Selfish Gene.
Intelligent life on a planet comes of age when it first works out the reason for its own existence. If superior creatures from space ever visit Earth, the first question they will ask in order to assess the level of our civilization is, have they discovered evolution yet? Living organisms had existed on Earth without ever knowing why for over 3,000 million years before the truth finally dawned on one of them. His name was Charles Darwin. To be fair, others had had inklings of the truth, but it was Darwin who first put together a coherent and tenable account of why we exist. Darwin made it possible for us to give a sensible answer to the curious child whose question heads this chapter: why are people? We no longer have to resort to superstition when faced with the deep problems. Is there a meaning to life? What are we for? What is man? After posing the last of these questions, the eminent zoologist G.G. Simpson put it thus: "The point I want to make now is that all attempts to answer that question before 1859 are worthless, and that we'll be better off if we ignore them completely."
What you're sort of saying in that paragraph, I think, is that evolution is the meaning of life. Do you want to start by exploring that, or do you want to answer the question, what is life, first?
If you look at living things as compared with the ordinary products of physics, they're just miles apart, and yet at no stage ever are the laws of physics violated. Yet somehow, never violating the laws of physics and chemistry, living things have moved an enormous way away in, what should we say, complexity space. The appearance of design. There must have been a kind of overlap between life and non-life when life first arose. But now all the life we know is just so many miles away from non-life that it's very hard to get confused. As for whether evolution is essential, I suspect that it is, but I mean, one's always got to be alive to the possibility that somewhere in the universe there's something else that you might describe as life because it's highly complicated and carries an illusion of design that has not come about by evolution. I would be hugely surprised if that were true, but we only know one example of life,
right,
which is the one on this planet, which is all, I mean, every form of life that we know clearly has one common ancestor because the genetic code's all but universal.
And replication, which is very much the theme of The Selfish Gene, is that a characteristic feature of life, that rabbits make more rabbits and rocks don't make more rocks?
That's certainly true. I mean, I think I'd prefer to say genes make more genes and rabbits are kind of incidental to that. But yes.
Gene is a detour on the way. I mean, the rabbit is a detour.
The rabbit is a detour on the way. Yes, a rabbit is a fantastically elaborate detour for making more genes. Yes, I mean, I think that's absolutely right. Rocks don't make more rocks. If they did, then that might be a candidate for a new kind of evolution. And I mean, crystals grow, but they don't then split and make more crystals. If they did, if a crystal grew to a certain size and then split in half, and then each of those halves grew to a certain size, then you'd have the makings of the beginnings of life. But what actually happens is crystals just plain grow, and that's different.
And how do you think life began on this planet? You mentioned crystals, and there are some ideas that you had sort of mineral catalysts and things first. And there's a theory about clay, I think, isn't there? But basically, what's got to happen is something's got to harness energy to copy itself.
That's right. Copying itself is the vital step. Yes, surely that's got to be true. So nobody knows how life began, and maybe we never will. It happened a long time ago under very different conditions. But I think we can say that the key step was the origin of self-copying. That wasn't quite sufficient. It had to be self-copying in what you could call an interesting way. It's not enough just to have, say, an entity that makes copies of itself, there's got to be a population of alternative kinds of entity in order for there to be competition and therefore natural selection. And nowadays, of course, DNA has this extraordinary property of producing an indefinitely large number of separate entities, because the sequence of codes is all but infinitely different. But it's got to be that. If you ask the question, what properties would life have anywhere in the universe, I think my first answer would be self-replication, followed by Darwinian natural selection. We could ask other questions about whether it has to be a digital code like DNA, or whether that's necessary.
But you wouldn't expect that if you found, I mean, I'd like to get onto extraterrestrial life, because I think potentially that's the most extraordinary discovery that we will yet make, and maybe we will. But you wouldn't necessarily expect to find that it had DNA. You might find it had something else. And a lot of the properties of the genetic code look like what I think Francis Crick called a frozen accident. In other words, that it could have been a different group of bases that came together to spell out a code. You could even imagine completely different sequences of things on DNA. Whenever
I meet a biochemist, I always try to persuade them to try to dream up an alternative biochemistry, an alternative genetics. I mean, we are so used to the idea that you have DNA programming the sequence of amino acids making proteins. And it may be that that's the only way it would work. It wouldn't necessarily be the same genetic code. As Francis Crick said, that almost certainly is a frozen accident. But it does look, doesn't it, as though protein has got some very, very important properties that might have to be universal. As I understand it, what the important property of protein is that the one-dimensional sequence of amino acids, which in turn is specified by the one-dimensional sequence of the genetic code, the one-dimensional sequence of amino acids determines how the protein chain shall wrap itself up into a knot, which has a three-dimensional shape. And that three-dimensional shape is absolutely crucial for governing, controlling, by its enzymatic properties, governing and controlling the chemistry of the cell. And I think I'm right in saying that a protein is capable of coiling itself up into almost any shape you like, if only you could think up the right sequence of amino acids. And so, since it's three-dimensional shape that determines the catalytic properties of an enzyme, then you've only got to have the one-dimensional code to specify the one-dimensional sequence of amino acids to make the three-dimensional shape, which will then have the desired biochemical effect. Well, that's a very, very singular property of protein, and it may be that...
Doesn't RNA have that property?
It does, yes, and that's in a rather weak, attenuated form.
Yeah.
And that gives a possible clue as to how the whole process got started. Because, as you know, people have talked about the catch-22 of the origin of life. You've got to have something like protein to do the catalytic function. But you've got to have something like DNA to do the replication and the specification of the protein sequence, because protein cannot copy itself. Right. And I think the reason for that is that it is wrapped up in three-dimensional shape. Yes. And therefore, the one-dimensional sequence of amino acids is therefore inaccessible, because it's buried deep within the knot. So you've got to have something like DNA, something like protein, and how do you get one without the other? And the answer may be RNA.
This was one of the great bafflements before the discovery of the double helix, was essentially realizing that life had three-dimensional properties.
Yes.
And yet three-dimensional things can't copy themselves.
Yes.
You know, you can't, there are no three-dimensional photocopiers, as it were.
That's right.
And just to stay on Crick for a second, he said that given the number of, given the age of the universe, 15 billion years, given that this planet has only been around for the last third of that time, and therefore there were 10 billion years before, and given that we know that life appeared quite quickly on this planet, And given that we know how many planets there are likely to be, because we know how many stars there are, and we know they're likely to have solar systems, and that those are likely to include Earth-like planets in huge numbers, the chances are this wasn't the first place that life arose. And if it arose somewhere else first, the chances are it arose at least 7 or 8 billion years before it arose here. In which case it would have reached a sophistication where it could have started thinking about colonizing the rest of the Earth. Therefore, he said, we probably arrived here from outer space.